All right. Here's the first part of the wrap-up of the lab. We're going to kind of do this in two parts. All right, so here are the main things that you should be taking away from this, all right? So the first thing is you're going to have a graph. I'm going to put it in centimeters this time, okay? And when something is speeding up, you're going to see this upward facing parabola graph, okay? And the equation for me was like xf equals like 100, just kind of rounding my numbers, okay? Plus, I don't know, this was like 5 or something, t. Mine was actually minus t minus 0.01 centimeters, okay? All right. When you linearize your graph, like this is how we used to have to do it in the old days when we didn't have computers to curve fit it. I'm not even kidding, right? That's how you have to get it so you can calculate the slope. All right, you're going to go like this. So basically what you're trying to do is you're trying to find out what's the proportional relationship here, okay? So here, x is going to be directly related to time squared, okay? Assuming it starts at 0, which is pretty close, okay? Here, this is kind of telling you the same thing also, but you're seeing that squared in the parabola shape, okay? Here you're seeing the squared in the variable, all right? So this graph, you should have gotten something, I think mine was 104, t squared plus, I think mine was like 1 centimeter or something. We're just kind of missing that middle term in this one, but that's okay, all right? So number one thing you should see is that these are the same graph. These are the same graph, it's the same relationship, it's just a different way to get it, all right? This one just more cleanly comes from the y equals mx plus b, right? Where here's the key switch that you're making. You're changing that x variable to be t squared, okay? All right. Now, what we really want to do is compare the position and the velocity graphs, okay? So when I had this, okay, and I had xf equals 100 centimeters per second squared plus 5 centimeters per second t, oh, I keep doing that, minus 0.1 centimeters, okay? Now, your velocity graph should look like a line, okay? It should be linear, and it should have an intercept pretty close to 0, but maybe not quite 0, okay? So when you're writing your velocity graph equation, you would write, you know, you'd start with your y equals mx plus b because it's a line, okay? Your y variable would be the velocity, and we'll say final because it's going to be at whatever time. Okay, your slope here, all right, should have been, I don't know, should look something like this. Well, here, let me just not put the units yet. Okay, your variable here is t, okay? Plus, I'm just going to fake mine. I didn't actually do it. And I'm going to see what I think it would be. Okay, mine would be 5, just FYI, okay? And then the y-intercept would have units of centimeters per second, okay, because it's the y variable. All right, now, when we think about the slope of this graph, my rise over run, my rise is centimeters per second, and my run is seconds, okay? So this would be units like this. Okay, and you might remember this from freshman physics. This is how we would write it in freshman physics. So we'd say for every 1 second, right, that passes, the velocity increases by 200 centimeters per second. Okay, all right, so this centimeters per second also can be written like this, okay? I really prefer this, honestly, because it makes more physical sense what's happening, but almost everybody writes it like this. So your call, I don't care, it doesn't matter to me. I'm gonna just erase that little 1 right there. Okay, all right, so now what we wanna do is we wanna try to figure out what this graph is telling us. So we'll see some comparisons, okay? So let's look back at the position graph. I have all these numbers that I need to figure out what they mean, all right? This one's easy because you see the units are centimeters, all right? That is the y-intercept of this graph. All right, which if you remember from the last unit, that y-intercept is really just telling me the initial position. Okay, all right. This here is a velocity. This is a velocity, okay? On the velocity graph, it's a little easier to see because, again, my y-intercept, wherever this line crosses this axis, is going to be my initial velocity, all right? Just like in the x, its initial position. So that number hopefully should be relatively close for your data. But again, as soon as you start manipulating the numbers, the error just propagates through pretty rapidly, okay? But that, in theory, should be the same number, okay? So this equation here, I have v naught times t, okay? This is plus x naught. Okay, let's keep working our way back. Oh, God, I forgot to write t squared. Holy Lord, t squared. If it was a real class, you could have caught that. Okay, so here's my t squared. So I'm trying to figure out what this number in front is. Okay, and here I have t, and I'm trying to find this number in front. All right, so this is clearly not the same number. This is not even close enough to consider the same number, right? So it does have the same units, however. Okay, so it's sort of measuring the same thing, but one of them is going to have like a constant in front of it. All right, so we know from this graph, okay, when I say this in a sentence, 200 centimeters per second, for every 1 second of time passing, okay, the velocity increases by 200 centimeters per second, okay? This is what we call acceleration. All right, it's how much the speed is increasing over time, all right? So this number here is telling us the acceleration. All right, so this whole equation then comes out to be this, all right? And this is a super nice, clean y equals mx plus b coming from this graph here, okay? All right, so here's the interesting part, and you probably won't believe this, but I didn't know that this was true until I had a degree in engineering and a master's degree in teaching and an EDS in teaching, and I taught AP Physics for a year until I went to this workshop and somebody clued me in that this here is just half of this value, okay? So this equation is going to be 1/2 a, right? Because it's still a, because the units are the same, but this is just 1/2, all right? So this is how we get this interesting equation right here. Okay, now, those of you that are calculus people already, you probably sort of already know this and you see where this is going with the calculus, with derivatives and integrals and such. Okay, but we're not quite there yet for everybody, so just hold on to that thought. Okay, so these are the two equations that we are getting from these graphs. Okay, this is simply the quadratic equation from the position graph, right? This velocity equation is simply the y equals mx plus b from the velocity graph. That's exactly where they come from. All right, so you need to understand how those are created, and a lot of the graphs in AP Physics sort of follow these same principles. So if you really, really understand motion graphs, you could get things right on the AP test without understanding the concept, but being able to like draw the analogy to the motion graph. Okay, so just kind of keep that in mind. Okay, all right, so that's the equations we're going to get. We'll do the rest in the next video. All right, so make sure you understand this and where it comes from. Okay, it's really, really important.